Greetings from SJB Institute of Technology. I am Anita, working as an associate professor in the Department of ECE, SJBIT. Today we are going to look at Module 5 of microwave and antenna subject, and it is majorly discussing about the different types of antennas. Looking into loop antenna, horn antenna, aguda antenna, parabolic dish antenna, and helical antenna of different kinds. So these are the contents which I am going through: loop antennas and its radiation resistance and directivity, and the silent features of it, followed by horn antenna, rectangular horn antenna, and antenna types, aguda array, and so on so forth. So first we'll start with aguda antenna. Aguda antenna, as it is named after the invention from Professor S. Uda and Professor H. Yagi around 1928, and it is familiarly known as the Yagi antenna, and it is an end fire type of an antenna, indicating that the radiation is along the direction of the antenna. That means if it is placed along the vertical, the radiation pattern is also along vertical, and it is majorly used for TV receiving applications. In earlier days, we will be making use this as a TV receiving antenna, and it is used in majorly VHF and UHF bands, that is ultra high frequency and VHF frequency bands, ranging from 30 MHz to 3 GHz, and it is of very simple, low cost, relatively high gain antenna. Majorly it consists of three elements, basic aguda antenna consists of three elements, namely the driver element or driven element, and the reflector element, and the director element. So actually it is a resonant type. Resonant meaning it resonates only at one particular frequency. Actually it is a lambda by resonant antenna. The basic driven element, which is placed horizontally, known as an active element. Usually it is of length lambda by 2 indicating half wavelength. In order to convert that bidirectional dipole into an unidirectional dipole system, the passive elements which are used in before and after, behind and before that driven element, known as reflector and director. So these are passive elements, that is, reflector and director are passive elements and are placed in parallel to the driven element, collinearly placed together, which is shown in figure. Here you can observe. So this is a driven element. So this is a driven element. This is a driven element, and these are the directors, and this is a reflector. As it is indicated, the length of this should be lambda by 2. The driven element length is half wave dipole antenna. For a half wave dipole antenna, you will get the radiation pattern as a bidirectional downward shaped. I need to convert that to unidirectional radiation pattern. That can be done by placing directors in front of the driven element and placing a reflector at the back side. So the reflector, which should be having a length L value greater than lambda by 2, whereas the director's length should be less than lambda by 2, and in turn giving a radiation pattern as an end fire. That means, as we have placed the antenna in this direction, the radiation pattern will also be in the same direction. So we are getting a radiation pattern of downward shape has been converted into a single side. So this side is an unwanted one, which we need to eliminate it. That we can do by placing more number of directors, and this is known as an E-plane radiation pattern. We have different types. It is one of E-plane radiation pattern. Now the coming to the design parameters, as I have told. The parasitic element, that is nothing but the director, which should have a length usually less than length of the driven element by 5%, less than the length, whereas the element which is placed at the back side, known as reflector, whose length should be greater than lambda by 2. Coming to the spacing between the elements, which should be range between 0.1 to 0.3 lambda. So these are for a particular basic Yagi antenna, which has to maintain the driven element, director and reflector length, as you can observe. So the parasitic element means with the parasitic elements, the impedance which usually reduces in order to enhance the radiation resistance, we can go with folded dipole kind of driven element, where the impedance can be increased by replacing the dipole antenna with a folded dipole antenna, which is of this kind structure, and by adding a director in front of the driven element, each driven element, each director, which might give about nearly 3 dB gain increase. Usually the number of elements in an Yagi antenna will be restricted to maximum of 11 elements. So as we have seen, basically 3 types of elements that we will have in Yagi. One is driven element, reflector and director. So driven element is the one where you will apply the power. It is an active element, and usually it is a half wave dipole, or sometimes it can be folded dipole, because of the inclusion of the elements, the resistance might decrease. To enhance the radiation resistance, we can go with folded dipole. Coming to the reflector, which is usually we'll have only one reflector, which is placed behind the driven element, and the length should be slightly greater than the driven element, and it radiates. What it will do is it reflects the energy which is radiated in the backward direction. Typically, by adding a reflector, you can improve the radiation in forward direction by about 4 to 5 dB. Coming to the director, you have more than one directors which are placed in front of the driven element. By adding each director, you can increase the gain of about 1 dB to 3 dB in the forward direction. And coming to, these are the silent features of Yagi antenna. The parasitic element, as we have seen, if the length is greater than lambda by 2, that means reflector, and it acts like an inductor. As we know that in inductor, it lags the current, and capacitive means if the length is less than lambda by 2, that is the case of director, acts like a capacitor and it leads the current. As we know, in case of normal, suppose if in case of a capacitor, if you consider, leads the current due to the induced voltage. Current lagging and current leading effect, which will be seen by having a length greater than lambda by 2 or less than lambda by 2. By properly placing these elements with length less than lambda by 2, each one will excite the next one. As these are parasitic elements, directors and reflector are a parasitic element, no energy will be directly given to that. They each means it will be excited based on the electromagnetic fields that you will get from the previous element. Coming to the reflector, as I have told you already, it reflects the energy in the forward direction. Backward direction, it reflects, means it eliminates the radiation in backward direction. The greater the distance between the driven and the director elements, greater will be the capacitive reactance, and we need to provide in such cases corrective phasing of the parasitic elements. The length of the element while choosing it must be tapered to achieve the reactance. Actually, it is a directional antenna with adjustable front to back ratio, F to B, FBR we call it as front to back ratio. These are the typical values of an Aguda antenna. These are the ones you can observe. First one representing the director length, which should be around lambda by 2, 0.5. So in practical cases we can go with choosing the recommended value as 0.43 to 0.44 lambda. Coming to feeder length, so that is a folded dipole antenna or the direct means a driven element what we have discussed, it should be 0.5 lambda by 2. The director length less than lambda by 2, so this should be around 0.48 lambda by lambda, that is recommended value. Coming to the reflector, it should be greater than lambda by 2, that is it mean between 0.5 to 0.525. The recommended value is this. Then the spacing between the reflector and the feeder element should be between 0.2 to 0.25 lambda, and in between the directors you can have a spacing as 0.3 to 0.4 lambda. So it is the graph representing the directivity enhancement in case of Aguda antenna by increasing more number of elements. How it varies, one can observe this 3 element antenna, that is consisting of one reflector and one driven element and one director. With that we could be able to achieve a maximum gain of 8 dB. Further increase in number of elements of the directors, we won't increase reflector, we'll keep on add directors. Further increase in number of elements will have a slight increase in gain value by 1 dB usually. Later, even if you increase more number of elements, the gain almost retains constant gain or directivity. So maximum number of elements that you can make use in case of Aguda antenna is up to 11 elements. These are some of the silent features. So it is the one majorly used in HF, UHF, VHF bands, providing a high gain, and it is of simple structure. It's of low weight and low cost and relatively narrow bandwidth, resonant type of antenna, and it gives you unidirectional beam width with moderate directivity. It is having a bidirectional radiation pattern of half wave dipole is converted into unidirectional radiation beam. So the bandwidth is increased between 2% by increasing the spacing between 0.1 to 0.15 lambda. It provides a high gain about 8 dB with the 3 elements only, and giving a front to back ratio as 20 dB. That means maximum radiation will be in front direction compared to the back direction. Aguda antenna, which we also call it as a super directive or super gain antenna, as it is resulting a high gain. So if the directivity, if we need a directivity more, I need to increase more directors. So Aguda antenna is a fixed frequency device, frequency selective, and bandwidth maximum up to 3% can be achieved. So this is a diagram which is representing the Aguda antenna. One can notice, so this is a driven element and this is a reflector, and all these are directors, so which is mainly used as a TV receiving antenna. Earlier days we were making use of this type. Coming to the next one, helical antenna, we'll see that in the next lecture. Thank you.